All right. And just so everyone knows, this presentation will be recorded, and so there will be a copy of the presentation or the recording link sent to everyone afterwards. But thanks for joining. My name is Anthony. I run a company called Priopta. We focus on embodied carbon, whole building lifecycle assessments. We advise on policy and do various research projects as well. And so for today's presentation, I'm going to be going over this embodied carbon tool database comparison report that we published maybe about 2 weeks ago. Um, First off, I want to thank the National Research Council. So Mehdi, Davoud, and Heather from the National Research Council that's been involved with this project, that's also funded this project. Thank you for your contributions and in helping this project come to life. To give you some background on what this report and what this study was all about is we're looking at five of the main software tools that are commonly used in North America for quantifying embodied carbon at the project level for buildings. So we're looking at Athena, Beam, Tally, EC3, and Click LCA. And one thing that sometimes people find when they're doing whole building lifecycle assessments, when they're modeling a given project, and sometimes they try to model it in two different software tools, even with the same material quantities, they get different results. Sometimes those results are very different. Sometimes they're just slightly different. But and we might publish case studies for why that there's a certain discrepancy for a given project when it's modeled in two different tools. But we've never really gotten to the source of where those discrepancies really come from. And also, more importantly, how do we reconcile this? How can we reduce the level of discrepancies that we see in those results afterwards? And so this report, this study was an attempt to look at the material level, the underlying databases that are used in all of these tools and how they compare. Where is the discrepancies coming from across all the different life cycle stages? And through looking at that information and that data, hopefully we can come up with some recommendations for how we can drive alignment and consistency in these results in the future. Just some logistics for today's presentation. This is a 90-minute presentation, hour and a half. I'm going to aim to finish the presentation in an hour, and so that we have lots of time for Q&A at the end. If you would like, you can add your questions in the comments as we go through, as questions arise. Although at the very end, my preference would definitely be to get people to unmute themselves and just ask the question directly, and then we can kind of engage in a bit of a conversation there. Also, what may be a bit unique is beyond just doing question and answer, I'd like to actually have a bit of a discussion, maybe even a brainstorming session on like the next steps. What can we do to drive alignment in Canada? What might it look like if there were joint efforts in the US as well to kind of create alignment in the modeling assumptions that the tools use, right? So I'd love to have a bit of a discussion on that front or get any input and ideas for how to go about doing that as well. So yeah, feel free to write your questions in there and let's dive into it. So for some background context, in Canada, there are various different embodied carbon policies and requirements. And perhaps what's a bit more unique over the past few years is that in Canada, as opposed to what's happening in the United States, a lot of the policies were more focused at the project level. So looking at whole building lifecycle assessments. This is not universally true, and obviously there are other efforts in the US as well that we're focusing on this. But given that we have had this focus on whole building lifecycle assessments, there's a certain class of challenges around like where are the discrepancies coming from the different tools when we're looking at a whole building LCA, because some of the different tools make different modeling assumptions and default values and whatnot as well. Now, in Canada, probably most importantly, right now there's a current conversation to put embodied carbon requirements into the next national model codes in 2030. So in the 2030 code cycle, the idea is that there would be embodied carbon requirements that's still being discussed with the task group and kind of defining what the requirements would look like and all the details to kind of get fleshed out through there. But needless to say, to put something into the National Building Code, this is a very high bar, and we want to increase confidence in the results. And especially if the policy allows for multiple different software tools to be used, obviously we would want more consistency in the results across the different tools. And so this report is one step in that journey on how can we actually first identify where are the discrepancies coming from, and then how do we drive alignment there. There's also the City of Vancouver. Some of you may be familiar. It was the first jurisdiction in North America to have embodied carbon requirements into the building code in Vancouver. Currently, it's more of a disclosure requirement, effectively, but there are going to be reduction requirements in the future that are proposed, or that are being planned for. Similarly, in Toronto, there's the Toronto Green Standard version 4 that also has absolute embodied carbon limits for different types of buildings. So kilogram of CO2 per meter squared thresholds. I should note that in the Vancouver approach, there's a % reduction from baseline or an absolute threshold, like kilogram of CO2 per meter squared approach. And so regardless of which path you go, it still is important to actually have consistency in the modeling results across the different tools, because it'll affect whichever path you go on that. You have at the federal level with the Treasury Board Secretariat, they have embodied carbon requirements for federal projects, 30% reduction requirements for projects, and also some specific requirements for concrete and steel specifically. And then you have green building rating systems like CAGBC. They have the Zero Carbon Building Standard version 4 that also has embodied carbon requirements. Also LEED version 5. It's now a prerequisite to do this type of analysis. And then there's also certain points associated with different performance thresholds, right? So given all of this context, there's a lot of focus on whole building LCA or project level embodied carbon reporting. So how do we drive consistency there? Now, I'm going to touch a little bit on just the report structure. This is a fairly big report. If you've downloaded, you've probably seen there's like 200 something pages in this report, many graphs. So I just want to give you a quick overview on the layout of the report. And in this presentation, I'm just going to give a high level overview of each of those different sections. So first off, there's the introduction section. We talk a bit about the methodology, give an overview of the different tools. So all 5 of those tools, some high level descriptions on how they model different life cycle stages, et cetera. What's unique is we actually have this material coverage chapter or section that is the first snapshot that I've seen of actually like the number of data points that are shown per material category at a very granular level and how they compare across the different tools, so that we get a sense of just how much data there is in the different tools, but also the level of coverage for different categories of materials. Then we dive into selecting 39 product categories. And for each of these product categories, we compared relevant data points in each of the tools on a few different dimensions. So we look at the GWP, global warming potential or embodied carbon, at the module A1 to A3 phase. We also look at from module A to C. We look at the A1 to A3 impacts for the other environmental impact categories. So beyond GWP, looking at acidification potential, eutrophication, et cetera. And then we also look at biogenic carbon, how they're modeled for a few wood products. Then we get into the next section, which is looking at the default modeling assumptions per life cycle stage across many different categories of materials. So for each category of material, what are the default modeling assumptions that they use for transportation in module A4? So what's the default transport distances? What's the default GWP emissions per mode of transport? If they model A5, like construction waste, what's the default waste assumptions that they use for different categories of materials? B4 service lifespans, what's the default service lifespans modeled in each of these tools? And how many replacements does that lead to in a whole building LCA with like a 60-year lifespan? And then we look at end-of-life modeling as well and some of the differences in results there. And then section 4 we go into some tool-specific sensitivity analysis. So looking at some tool-specific features that may be relevant. So for example, in One-Click LCA, they have a localization feature. So we look at different scenarios if you assume different electricity grids for some generic data points modeled by One-Click LCA, how that affects results. And then we look at, for example, One-Click LCA has different service lifespan scenarios. So we also look at those different differences in those service lifespans, whether it's like a technical service lifespan or commercial service lifespan, how they compare. And then different end-of-life pathways that are for a given material category and how they vary. And then for a tool like EC3, they also have uncertainty adjusted GWP. So we looked into like what's the scale of that uncertainty factor that they apply and the range of that per material category. And all of that tees up the final section, which is the conclusion. So it's just what are the key insights from all of this analysis? And most importantly, what are the recommendations and future work? So how do we drive alignment in the tools moving forward? And so as I mentioned earlier, if you joined later, I do want to have a bit of a discussion on this section specifically, like almost like a brainstorming on like, yeah, how should we move forward? How do we drive alignment on this? And I should note that there's an appendix section that is actually not shown in the public version of the report, but this is shown to the National Research Council. Effectively, for example, when we're looking at section 2, we have these 39 product categories. In the report itself, we're actually only showing, I think it was like 8 categories, 7 or 8 categories of materials, and the rest of them were put in appendix. One A for length, because that would have been a lot of more pages, but also there was some sensitivity on like how much data we're showing publicly. And so anyways, that data is available more just to use this data from this analysis to inform future work around defining default assumptions at the national level. Okay. Oops, sorry. So let's dive into it. For a quick refresher, when we're talking about life cycle assessment, there's formal definitions for each of these life cycle stages. So module A1 to A3, these are kind of the main results that we typically see from an EPD, environmental product declaration. That's like what a manufacturer might report on, like everything from raw material extraction, transport, manufacturing. And so we look at the variation in results in A1 to A3. So as I mentioned, we have a section looking at 39 product categories, looking at the GWP variation on A1 to A3. We look at those other impact categories, acidification, potential eutrophication, smog formation, et cetera. Biogenic carbon, we look at the A1 to A3 differences in both modeling of GWP fossil and GWP biogenic. And then we also looked at, the localization of the grid mix in One-Click LCA. That's the tool sensitivity section that I mentioned earlier, and then EC3 on uncertainty adjusted GWP. So all of that is looking at the A1 to A3 phase. We also look at A4 phase, so like the transportation, both the GWP per transport mode, the distances per material category, and also what's the combined A4 for each of these material categories. A5, I just want to mention, when we talk about A5, sometimes we're talking about various different things. So if you actually look at the latest ASHRAE 240p standard, they actually call it 3 different sections, A5.1, A5.2, and A5.3. A5.1 looks at pre-construction demolition. So like if there's an existing building on the project site and you demolish that and then you build a new building, what's the demolition related emissions for demolishing that existing building so that's A5.1. That's not covered in this section. Then we have A5.2, which is site energy use. Some of these tools will have allow for the user to input like the actual energy use on site, on the construction site. But typically you don't have those numbers until after the project is completed, like assuming you're actually tracking that, your general contractor is tracking that site energy use. So even though that there's some of the tools allow you to input that, there's no default modeling assumptions or values applied there, generally speaking, across all the different tools. So we didn't cover that in this case, in this report. So the section that we did cover was what we call A5.3, which is construction waste. So some of the tools, namely One-Click LCA and Athena, do have default construction waste factors per category of material. And so we looked at the variations in those assumptions. Then we have B4, which is the service lifespans and replacements. That's that phase. And then end of life, we looked at, the end of life emissions. And for One-Click LCA specifically, we looked at different end of life pathways that are available there. Okay, so in it as an overview of the different tools, we just to give some background context in case you haven't used all these different tools, Click LCA is the tool with the largest global database. I think globally they have something like 360,000 data points. Of that, there's about 200, a little over 200,000 data points that are specific to Canada and the US. Um, and they also have some, and a lot of those data points are environmental product declarations, both product specific EPDs as well as industry average EPDs. They also have some generic material profiles, including ones that they've modeled internally. I think internally they have something like 4,500 generic profiles modeled. I mentioned here that it uses EcoInvent for generic material profiles, but my understanding I learned later on is that I think that's true of like the older data, but may not be the case for the newer data, or it isn't the case for the newer data. So anyway, just some formality there. Then you have Athena. It's a free tool that's been available for many, many years. I think it's been around for more than 20 years. They have a smaller data set, mostly generic material profiles. I think it's about 500, a little over 500 data points. They don't have much manufacturer-specific EPDs. There are a few in there, but not very much. It has some regionalized data for Canada and US specific cities. Um, then you have Tally, which has been around for a while too. It's a Revit plugin. That data is mainly generic material profiles based off of Gabby, to my understanding. They do have some data points that are referencing, for example, environment, industry average EPDs, and maybe even a few product specific EPDs as well. And then EC3, a very large open access database. I think it's over 180,000 data points. Actually, I think it's over 200,000 data points now. At the time of the analysis, there was about 150,000 data points specific to Canada and the US. And I'll dive a bit deeper into that afterwards. And then we have Beam, which is mainly used in Part 9 construction. So like kind of single family homes and smaller scale residential buildings. They have a more curated data set, but it does have a lot of industry average EPDs and some product specific EPDs as well, about 800 something data points in there as well. So that's kind of an overview of the different tools. And then we go into, like, for example, in module A4, how do they model transport distances to the extent that they do model A4? So, and can the user override those default assumptions? So we kind of give some overview on that, descriptions on that. What different modes of transports are available? Are there more modes that they can select from, of like different modes of transport for road transport or rail or ship, etc. So we give some information on that. I'm not going to go in detail on every aspect of this, but you can read through this. Same thing, like how is site energy use addressed in A5.2? So like, can a user manually input it? Do they have default assumptions? I think Athena is the only one that has a little bit of A5.2 default assumption because they assume some crane energy use to lift some materials up. So, but that's a fairly small number, I think. And then you have A5.3 construction waste. How is that modeled? Service lifespans, are there different scenarios for service lifespans like Click LCA has? So we kind of give some overview per life cycle stage for each of the tools. Same thing with end of life modeling. How is end of life modeled? Can you override? Can you change different end of life scenarios? How is module D modeled? And then we go into some other things like biogenic carbon, localization of grids, et cetera, and future development plans. So that just kind of gives an overview. That was section 1.3 of like each of those tools. And now we go into section 1.4, material coverage. This, as I mentioned, to my knowledge, is like kind of the first snapshot that I've seen of like an actual detailed overview of how many data points exist per material category across all these different tools. And to clarify, we're only looking at the data specific to Canada and the US in this scenario. One Click LCA in the North American data set, or the US Canada data set, is like 201,000 data points. EC3 has 155,000, Beam has 825, Tally 692, Athena 525. And all of this is updated as of October 2025. So this is kind of a snapshot in time. And that's especially relevant for One Click and EC3. those are obviously the biggest databases, and those numbers are constantly changing. We actually further disaggregated that to look at how many data points were specifically available in the US and Canada. So you can see US obviously has a lot more data points. In Canada, there's 11,000. In EC3, there's 7,500. Okay, so that's kind of at a database level, but then what's important is actually understanding per material category. So to do this analysis was a crazy data cleaning exercise because, as you can imagine, all these different tools like structure their underlying data very differently. They categorize their materials in very different ways. So first off, we needed to kind of classify all the data points in a consistent format so that they're comparable, right? And so the way we went about doing this is like we actually have a three-level material categorization. At the time when we were doing this analysis, Click LCA only had a two-level material hierarchy. They didn't have a three-level. So we used their two-level material hierarchy as the material level 1 and level 2. Right now, I'm just showing you level 1. Imagine level 2 is like a more granular breakdown of that. And then level 3, we actually created our own custom schema for level 3 to get to that level. But in terms of data point counts, we show level 1 and level 2 and how that compares across the different tools. And you can see on a high level, concrete and asphalt, that's a lot of the data points, especially in EC3 and one-click. They actually make up 95% of all the data point counts when you look at EC3 and one-click LCA. The vast majority is the ready-mix concrete. These are like mix-specific EPDs for different sites and locations. So as you can imagine, they're usually generated by these EPD generators. So there's a lot of high volume amount of data on that. Similarly for asphalt as well. So I had to put them in a different axis because there's so many, it's a completely different axis. And then all the other categories, you can see how they compare across the different categories. And as I mentioned, and more is not necessarily better per se. Like for some of these, we also want to just look at what type of coverage do we have. For example, if we want to look at mechanical, electrical, plumbing in the future, or interior finishes, do we have is there coverage of those data points? And obviously, for some of these tools, when they just have generic material profiles, obviously they have less data points, but that means they're still covering that category, but they don't have like every manufacturer specific, product specific EPD, for example, right? So, and actually, to step back, I didn't mention this earlier. In this report, obviously, we're comparing a few different tools, but I want to emphasize that we're not trying to assess which tool is better. Each of these tools have different strengths and weaknesses, or we're not trying to assess which one is more accurate per se. There are discrepancies across these different tools, but to be honest, that's to be expected because all of these tools were developed independently in different timeframes, using different underlying databases in an environment where there was no standardization or coordination, no policy driving this type of initiative, no national alignment efforts or anything. So it's not a surprise that there are differences in these, but I think there is an interest among the tool providers, or there's an openness among the tool providers that if we were to kind of create some alignment on some of these assumptions, like they'd happily adopt those, right? So the point of this study is not to like point out what's better or what's worse or whatnot. It's more just to identify what does the data currently show, where are the greatest discrepancies, and how do we close that gap in the future? Okay, so I mentioned, so this was kind of looking at all the different tools. And then now I actually split it up for Canada and the US separately. So on the left side, this is Canada for EC3 and one-click. And then for the US, you can see the breakdown. Given that this is a Canadian funded project, we also were interested in just how much Canadian data there was, obviously. Okay. Next, we go into the section where I mentioned we're going to look at 39 product categories. How do they compare? So let's start off by looking at GWP A1 to A3 values. So this is an example of like for one of those material categories, how did they compare? And the overall premises for each of these categories, and we picked 39 product categories that generally cover the most important materials for like structure, envelope, and interiors to the extent that data existed. And the premise was that let's say you're doing a whole building LCA and you're trying to model a baseline building. So you're not necessarily trying to pick a specific manufacturer specific EPD or whatnot. You're just trying to model what is your baseline building. And oftentimes you use whether it's a generic material profile or an industry average EPD for that category, right? And so this is a good example. Let's say like ready mix concrete, 35 MPa concrete. If you're modeling a project, what data points would potentially be relevant in each of these tools? So for example, in one-click LCA, you might look at you have the industry average EPD for BC. Let's say this is a BC project. You'd look at those industry average EPDs, and there's one with air entrainment, one without air entrainment. So we're just showing that. Um, but then they also, one-click LCA has their own generic material profiles that are modeled too. And maybe a user might select that. And so we also included the generic profile from one-click. Athena, what data point would you select? They have a Canada one, but they don't have provincially specific numbers. So you would pick the Canada one. If you're using Tally, well, Tally doesn't actually have any Canadian data. So they only have the US NRMCA data. And so some people might pick the US national data. Uh, if this is a BC project, maybe they think, well, it's close enough to the Pacific Northwest. Maybe we pick the Pacific Northwest number. So then you can see, obviously, there's differences in those numbers there. EC3 has the same industry average EPDs that one-click has, and then Beam has that as well. And then they also have an older version that's shown like the older CRMCA national Canada numbers as well, right? So you can see a few different numbers that are potentially that you could pick, right? And so generally to figure out the discrepancy, we're not trying to say which number is right, but we're just trying to get a common point of reference. And so given that one-click LCA has the largest amount of data points and most coverage of the different categories of materials, we generally just picked what was the latest industry average EPD in one-click LCA, and we just use that as the point of reference. So you can see this reference, the little arrow. So we pick this data point, and then you can see this dotted line. So that dotted line is set at there. So you can imagine if you compare every data point, you could see what percent difference there is, like less or what percent greater it is relative to that common reference point. So that's generally how we kind of conducted the analysis. So later on, I'll show you some graphs to just show you the percent deltas. So this is like ready mix concrete. So in this case, you can see there's variation because of regional differences and just what data is available in the tool and how regionally specific it is. Then we look at something like rebar, for example. So again, you can, in one click, you could use the CRSI industry average EPD. You could also use the generic profile. And if you use the generic profile, it's very significantly different. And so there's a big delta there. And then the other ones actually agree pretty well. But you'll see, for example, Tally. They actually also reference the CRSI, the same industry average EPD, but they're referencing an older version. So there was a newer version that was published in 2022, and this was the previous one. Oh, sorry, the previous one. And so the previous one was a little bit higher, right? So sometimes it's like a certain tool may not have the latest data available, even if it's referencing the same kind of type of industry average EPD. So that can be a source of discrepancy. And then, yeah, we have steel as well shown here. So sometimes, generally, the generic profile data from like Athena or Tally, or even the internally modeled ones in one-click LCA, you can see some discrepancies with those compared to the industry average EPDs. Again, not saying which one is right or wrong, but it's just they're different data points, and sometimes they agree, sometimes there's significant differences. So this is just an example of some of the categories of materials, what the detailed analysis looks like on each of the categories. And so what happens when you just look at this across all the categories? So I mentioned we picked we picked 39 product categories. So this is the part one of this. There's a second version of this. So each row is one category of material, like clay bricks or ceramic tiles or Portland cement, carpet, wood flooring, rubber flooring, gypsum, etc. So each of the different types of insulation, fiberglass, mineral wool, EPS. And as you'll recall, I said the reference that we set was generally the industry average EPD from the latest one from one-click LCA. And so you'll see a lot of data points that are 0%. That's the industry average EPD. But then you'll also see some that sometimes there's a big percent difference even within one-click LCA. And that's usually the generic profile that's modeled in one-click LCA. And so you can see some big discrepancies there. And so that's usually what you see there. Like, so the way to read this is like if you see 102%, that's like 102% bigger than the reference, or minus 80% is like 80% less. So you can see the same thing for Athena and Tally, the percent deltas here. And because Athena and Tally mainly have generic profile data, and Athena mainly based on EcoInvent, Tally mainly based on Gabi, that can vary from like the latest industry average EPD. right? So sometimes you'll see for these different categories, you'll see this type of percent delta. EC3 usually has the latest industry average EPDs, but sometimes for various reasons, they don't have the exact same EPDs or the latest version, or maybe one click doesn't have the latest version. So like there can be some discrepancies in either way there. And then Beam similarly. Um, Okay, so that's like the first, and then this is the second half of that. So these are all the other material categories we looked at. So like, uh, roofing membranes, plastic membranes, precast concrete, cement boards, ready-mix concrete I showed you earlier, different types of steel, aluminum. So again, you can see the discrepancies here, and so just at a quick scan, this is I spent a long time to come up with these graphs to like get to a point where we could actually distill it down to like across all 5 tools how to show the discrepancies on all of these. So this gives you a sense. A1 to A3 GWP. This is the level of variation that you see. So as I mentioned earlier, what's the sources of these differences? Well, I got to go faster. I'm going a little slow. Okay, what's the sources of these discrepancies? It could be regional specificity. Maybe for a given region, they don't have a certain tool doesn't have the regionally specific data, like Tally doesn't have Canadian data. There's obviously big variations between the generic profiles versus EPDs. Generic profiles may be modeled to try to model like what is like typical rebar at like 97% recycled rate or something. But then an industry average EPD will actually look at all the different manufacturers and try to have some representation and maybe have some production weighting for how representative this is of all the manufacturers as part of the industry association and create an EPD, right? So there are many reasons why there are discrepancies in these results. And then, there can be outdated EPDs as well. And obviously there's discrepancies there. That's like the rebar scenario. So, yeah, that's on a high level, some of the types of differences that we see. Now we can look at A to C. So not just looking at A1 to A3. And so what the detailed analysis looks like is kind of similar type of graph, but instead of just showing you A1 to A3, we show A4, A5, B1 to B5, and then module C. So for example, for wood, in this case, we have cross-laminated timber, glulam, and softwood lumber. And you can see, for example, in Tally, like the end-of-life modeling for wood can be quite high, quite a bit higher than some of these other categories. We can get into that a bit later, but they have different ways of modeling end-of-life. And yeah, so we'll get into that later. And for softwood lumber, for example, I noticed that they had a lifespan of 30 years instead of like the building lifespan. So that created a replacement at 60 years. I later found out that may not always be applied because I think it's in the data that I saw, it was basically like it said 30 years as a lifespan, but I think it's also some connection with like the assembly level estimate, like depending on what assembly element it is, it might get overridden. Anyways, but there can be discrepancies in some of the modeling assumptions on this, right? Okay, and then as another example of different category material, XPS insulation. And for those of you that are aware, there used to be HFC blowing agents, which are very high impact in the emissions intensity of these all the XPS and all the spray foam insulation in North America prior to 2021, or most of it actually had these HFC blowing agents, which was very significant. But one of the tricky things was where do you assign those assumptions or those emissions, because actually a lot of the blowing agents technically happen in some of it happens in module A5, some of it is in B1, but the way the tools were set up, they don't model B1 properly. Or they don't, because most materials don't have a B1 like kind of use phase emissions, like they don't typically just off gas emissions. But in the case of blowing agents, they do. And so sometimes some of the tools actually had to roll up that B1 emission number into the A1 to A3 number to count it properly in their tools, right? So we just kind of show an example of that. And then also end of life, because there's some emissions of the blowing agents at the end of life. How do they model that? Do they just have some generic assumption for that tool or for that product category, and they apply some emission factor there? Or do they actually take the blowing agent impacts that are shown in the EPD, which is shown in the module C, right? So these are a little bit of nuances, but just kind of highlighting those types of differences. And so we looked at those types of things as well. Yeah, I won't get into that. And then we looked at all 6 impact categories, or well, the other 5 impact categories beyond GWP, looking at the A1 to A3 impacts. So Yeah, so for refresher in North America, using the Tracy 2.1 method, we look at six environmental impact categories in LCA. So I have global warming potential, which is what we refer to as embodied carbon typically. But then there's also, sorry, what just happened there. Okay, then we have acidification potential, eutrophication potential, smog formation potential, ozone depletion potential, and depletion of non-renewable energy. Um, This is mainly so most policies that I see in North America has mainly just focused on GWP, and I think that is likely the right call. We did have a lead version 4.1. They did have some requirements to look at these other impact categories, and you couldn't be more than 5% above the baseline. But that actually caused some problems because we're assuming that this data is like really consistent and comparable, and especially when you're comparing up creating a baseline and measuring percent deltas, sometimes that would get tripped up. Like a mass timber project might still get tripped up on eutrophication, depending on the EPD, or even low carbon concrete mixes that are very much lower on GWP. Sometimes they would get tripped up on some of these other impact categories. So we wanted to kind of look at this. And so we look at similar format, but instead of just looking at GWP, we look at the variation across all the different impact categories. And so you can see for some of these categories, there can be significant differences. Like let's say for glulam here, right? Eutrophication, you can see like there's big differences in the numbers for eutrophication, right? Or same thing with like softwood lumber. And all that to say is that I think this data, just looking at across all the scale, there is huge variation in these other impact categories. And so, not to say that these impact categories are not important or that we shouldn't look at it, but just the data reliability is such that it's very hard to develop policies to point to this because like there's such huge variations in this. And this could be kind of stemming from the upstream lifecycle inventory databases that are used. You know, some EPDs may use Gabi, some use EcoInvent or some other LCI data as well. It could be a whole host of reasons why there may be discrepancies, but the short answer is that or the short summary is that there are huge differences. So much so that I had to change these graphs. So these graphs, if you remember the GWP graphs, they were framed as increase or percent decrease relative to the reference. In this case, they needed to be framed as like multiples. So like if you see a positive number, it's a positive multiple. If it's a negative number, it's a negative multiple. So like if you see negative 50, that means it's 50x smaller than the reference. Or if it's like a positive, I don't know, like positive 5 or so, well, that's positive. Anyways, if it's a positive number like 16, then it's like 16x bigger. And so eutrophication, there's a lot of differences as I was showing here. Like, you know, we have some that are like negative 286x, and we've seen numbers that are like thousands of x bigger or smaller, right? For example, for ozone depletion, that's probably where the biggest variability is. But like these are very, very tiny numbers, so the percent deltas can be quite significant. So all that to say is that I think it's best if we don't include these other impact categories because there's such variability in these other impacts categories. And I think lead version 5 has addressed that now. So I think you still report on it, but they kind of removed that requirement. My understanding is. Okay, so that's the other impact categories. Then you have biogenic carbon. And so, you know, some of generally speaking, we should try to report this separately. And you know, some policies may include the accounting of the biogenic carbon. Some of them just have a disclosure requirement, but like you keep the reporting separately. Regardless, I just wanted to highlight how is biogenic carbon modeled in these different tools right now? How is it shown? So this slide just shows you GWP biogenic only. So there's a difference between fossil and biogenic. So the GWP fossil for wood products would be like if you what's the energy related emissions from like extracting or like harvesting the wood, transporting the wood, heating the kilns for the production of the wood or manufacture of the wood products. So in this case, we look at CLT, glulam, and softwood lumber, and just looking at the biogenic flows. So like this is so basically for any bio-based materials, there's a certain amount of like carbon content in the wood. And so how do we account for that? Sometimes people talk about like the stored carbon in the wood and you know delaying the emissions in long-term long-lived wood products. Okay, so this is breaking down GWP biogenic only, looking at the different life cycle phases. And so you can see the A1 to A3 numbers, um, relatively consistent. I mean, there's obviously discrepancies between these, but then you see, for example, one is like really high. In this case, this was the latest industry average EBDs from the Canadian Wood Council, where they have provincially specific. So BC, Alberta, they have like specific numbers in the latest 2025 EPDs. But I noticed like it was actually quite a bit higher. Like this is like 1,500 something instead of like 800 something. I'm only highlighting this scenario is because like sometimes there can be like data entry errors in these tools or for a variety of reasons, right? So all that to highlight that we also need to think about quality assurance and like how the data is entered in. And I can also empathize with some of the tool providers. It's actually very hard. EPDs are published oftentimes in PDF reports. How do you parse that properly? And sometimes there's no standardization in how they format stuff and whatnot. And so in this case, what happened is that I think the latest EPDs they report in module A3, they have co-products. So they actually showed the biogenic carbon impacts of the co-products. So this is co-products that leave the product system. So like not the like in the full log, there's a certain not all of it makes it into like the lumber in the final building. So that they also have like the co-products that get used for I don't know other products like for paper or I don't know wood pellets or whatever, right? And so they showed that number, and so like they basically didn't capture the right number. They summed up the A3 number with this module C number, and so that there's a much higher number there, right? One-click's already been alerted to that, but all this is not to say like oh they did a bad thing or whatever. It's more just like to highlight that especially with the volume of data that we're looking across all these EPDs, we need to think about the quality of the data input as well, and how do we get quality assurance in that. Okay, so there's that. I mentioned earlier, module C. They also have differences in how they model that in Athena and Tally versus one-click LCA. So that was biogenic. And then this is a graph that shows you like if you put all of it together. So if you have biogenic only, that's this side, and you sum it across all those life cycle stages. So you have a stacked bar graph of all those life cycle stages. The black bar showing you the net impact for GWP biogenic only. Then you see it for GWP fossil only. And then if you were to combine them to get a net number, and I'm not saying you should, but that I'm just highlighting what it would show, you'd kind of see this, right, across module A to C. So all this to say is that like I think we need more consistency in how we do biogenic carbon modeling, even if it's just like disclosure only requirements. But yeah, across the different tools. Okay, I need a sip of water. All right, next up. Oh, okay. Life cycle stage assumptions. So looking at module A4, transportation to site, there's different modes of transport available in the different tools. So for example, this is, this is the road transport. So like, for example, one-click LCA might have a concrete mixer truck, a dump truck, trailer combination. Athena has like diesel road, short haul or long haul. So this is the GWP factor, kilogram of CO2 equivalent per ton kilometer. So depending on what mode of transport you select, for each unit of mass to transport it 1 kilometer, what is the GWP value? And so this is the first layer of where I think we need consistency. And actually, in doing this, I realized that EC3 has really high truck numbers, both for concrete mixer truck and their truck unspecified. And these are the modes of transport that are available, that are used in the default modeling assumptions when they're modeling A4, for example. You can see it's like almost 3x higher than some of the others, right? So obviously, if you have discrepancies there, even if you have the same distances, uh, it's going to have much higher emissions. Similarly, you could see, well, in this case, we're looking at rail and then shipping as well. I would say most of the data points and the default assumptions for most of the categories of materials, it primarily relies on road transport. So this is the most important variable. And actually, in doing this analysis and looking at this, by spotting these numbers, I also highlighted this in a draft comment for the draft ASHRAE 240p because I think they were about to use numbers that were very similar to this. And yeah, so all that to say is like we need to standardize on these assumptions. Um, and so keep this in mind when we're kind of looking at this analysis later. So for example, like In Tally, they just have a truck number, not they don't have a specific one for concrete mixer truck. So like, there can be big differences in those numbers, between like this versus this, right? So then the next thing is transport distance. This graph may be a bit hard to read, but basically what we did was like at the material level 2 categorization across every category material, we looked at what's the default transport distances of the tools. So the different colors represent the different tools. And I just want to highlight ready-mix concrete in particular. Even though the numbers seem very small in this graph, because obviously, for some categories materials, there's like thousands of kilometers of transport distance. But in this case, because ready-mix concrete is like 90+% of the mass of the building, even though these distances are short, they make up a significant fraction of your A4 emissions. And so the default transport assumptions are very important. And so we have a scenario where Tally assumes by default 24 kilometers. Then you have EC3 assuming 51 kilometers, Athena assuming 60 kilometers, and then Click LCA assuming 200 kilometers. That's obviously going to lead to discrepancies in the results, right? So in addition to like standardizing on what the GWP is for each mode of transport, we need to standardize on the default distances. Now, I'm not saying we should come up with that you can come up with one default distance that is applicable for every single project. Projects should be able to manually override this if they have better data, but we need consistency in the default assumptions in the tools. So this is an example of one thing, right? It's like the transport distance is big discrepancies. And then if you combine those two earlier factors, the GWP of like, for example, the concrete mixer truck, and then combine that with the transport distance, this is the range in the emissions. So there can be very significant deltas, even like in this case of looking at ready-mix concrete between the different results. Okay, so that's A4, then A5, construction waste. As I mentioned, I think only Athena and Click LCA actually has default construction waste factors. This is A5.3 that I mentioned earlier for construction waste. So essentially like whatever amount of material that makes it, let's say like concrete, there's a certain amount of concrete that makes it into your building, but you actually over order a little bit and there's a little bit of waste on site or whatever. So that maybe like by default, they assume 5% additional kind of a site waste factor, right? So this is what this number refers to. And so you can see for some categories of materials, there are big differences. Like for like aluminum, it's like 7.5% versus 1%. So for some of the metals, we see some bigger discrepancies in these assumptions. Similarly for wood, Athena might be assuming like 5% or 1%, but then Click might assume 16 or 17%. So again, there's another source of discrepancy. I think we can drive alignment on this, but yeah. That's A5 construction waste. Then we get into service lifespans. So for each category material, what is the default service lifespans? So only Athena, Click LCA, and Tally have default assumptions for this, modeling for module B4. So the way to read this graph is that we have the different colors for each of the tools for each category of material. So in this case, we're looking at doors, windows, and partition systems. So for example, like different frames of material of windows. Let's say like for example for PVC windows, right? Athena assumes 18 years for the PVC window service lifespan. Click assumes 40 years. Tally assumes 30 years. And then this red line is at the 60-year mark. So in a whole building LCA, typically in North America, we standardize on a 60-year lifespan for the building, just for the purposes of comparability, right? So let's say you have 60 years. Then this is the service lifespan. And then on the right side of the graph shows you the number of replacements at 60 years. And so you can see if you have an 18-year assumption, it leads to 3 replacements. If you have 40-year or 30-year, then you have 1 replacement. So this is at different thresholds relative to the 60-year mark. If you're kind of just under it at certain thresholds, it can have implications on the number of replacements. So I think we need to think through like what are the default assumptions for that? Can we standardize on these types of assumptions, right? Yeah, this is basically showing the same thing. Oh, just one mark is that like sometimes I show 100 years. That doesn't necessarily mean that in the tool it says 100 years. That's just my shorthand way of saying like the lifespan of the building, because sometimes they just call it certain building lifespan or something like that. So usually for most structural materials, it's assumed at 100 years, for example. So that's surface lifespan. Then end of life modeling. So there's different ways that the tools modeled end of life, and this is a bit trickier. I kind of created my own taxonomy for different end of life categories. So broadly speaking, downcycling, incineration, landfilling, mixed end of life, so multiple different paths of end of life, and then recycling. And then as a tier further, it may be more material specific. So for example, incineration of bio-based materials or incineration of plastic makes a big difference. Are you looking at landfilling inert materials or blowing agents or bio-based, et cetera? So I kind of, based on the information that I had, and sometimes I had to make some interpretation or judgment to kind of classify these, I tried to categorize them for each of the tools. Now, for example, for Athena and for Tally, for some materials, it's not like they just have one end of life pathway. Like it all gets incinerated or it all goes to landfill. For example, for wood products, they'll assume a certain percentage goes to landfill, a certain percentage gets recycled or reused, a certain percentage goes and gets incinerated, and then even how they model that will be different too. So like for wood products, in particular, that's a bit trickier thing, right? So like if you landfill, what percentage of that wood decomposes and then turns into methane, and is there landfill gas capture? And then how much of that goes to the atmosphere, and how is that all modeled, right? So there can be discrepancies in how all this is modeled. So this is just looking at the GWP emissions per ton. Now, you'll see some numbers that are super high here. This is really just the blowing agents. So this is, remember, XPS and spray foam with the HFC blowing agents. They're just looking at the end of life modeling from those EPDs. So that makes sense that these numbers are very high. So then in the next graph, I just try to cut off some of those. Like this axis was like up to, I don't know, 13,000 or whatever. But then I cut it off at 750 just to get a better visibility on some of the other ones. All this to say is like, yes, there's definitely differences in how this is modeling. One of the recommendations, I'm kind of shortchanging this, so one of the recommendations from this report is to create national default assumptions for each of these life cycle stages. So, A4, A5, B4, and Module C. I think those earlier stages are the easiest ones to come up with. Module C is probably going to be the trickier one. I think it potentially is still doable, but that's something that we need to explore. But ideally, we have some consistency in how we model end of life. Okay, then I mentioned there was some tool-specific sensitivity analysis. So I wanted to highlight a few features that can also affect the results. Sometimes some of these tools have additional customization settings that are available. So in this case, Click LCA has a localization feature if you used it. So in their LCA parameters settings, one thing that I've found is that by default, they have this. So they have this idea or this thing called localization, where basically they try to estimate the amount of electricity usage associated with the manufacturing of a category of materials. And let's say if you don't have better data or you want to localize this to a different region, use that same data point in a different region, you can change out the electricity grid carbon intensity from one region to a different region. And so this is and this is especially applicable to like the generic profiles that they've modeled internally, like where they create generic profiles for different categories of materials, like where they've internally modeled the whole LCA and they know the electricity assumption there and they can swap it out. One thing that personally I think maybe some people are not aware of, and I think we need more standardization around, is that by default they recommend to use their version 2.1, which includes material localization on everything, not just on generic profiles like modeled by Click LCA, but also on like product specific or industry average EPDs from different countries. So if you think in the Canadian context, we use a lot of EPDs from the US as well, including industry average EPDs that actually are relevant for both US and Canada, but sometimes they're classified as US EPDs. And so if you have this assumption laid on, it can sometimes like try to estimate the electricity grid impacts and swap it out for a Canadian electricity mix versus whatever was the origin, and change the reported GWP value in that EPD, which I personally don't think is a good idea, and would obviously affect the A1 to A3 results. And this actually affected a lot of our analysis early on before we kind of figured this out. And so my recommendation, especially for policy as well, is that like we disable material localization And you only use this localization feature for the generic data that they've generated for themselves, those generic profile data, which generally I don't think we need to use too much in Canada because there's usually a better industry average EPD to use anyways. Um, yeah, but that's a nuance, right? So like for policy impact, so for example, we've advised the city of Vancouver on developing their embodied carbon policy, and I've even recorded some tutorial videos for like submission process to the city of Vancouver. And so like I explicitly say like, if you're exporting raw data, also make sure you set these LCA parameters so that we can make sure that those results are more comparable, right? So this is just kind of like some of those nuances that like you could set policy, but if you have no visibility or understanding, you haven't used all of the different software tools and how these things can affect those assumptions. I think it's important to highlight some of these things, right? And so you can change. This is an example of like how you can change the electricity grid impacts and whatnot. And yeah, but I think applying it on top of EPDs can be an impact. So, but in this analysis section, we're looking at just the generic data that One-Click LCA has created. And so just to give you a sense of like how this could look like. So these are the electricity grid carbon intensity factors that they have for different provinces as of 2023. I think it's based on StatsCan or something like that. So they have some numbers here, and even the grid factors can be different than some of the grid factors that we might use in energy modeling. But anyways, I've selected a few different provinces. So like I looked at the Canada National Grid, then the BC, Alberta, Ontario, Quebec, and then just for comparison's sake, just comparing it against what's the default US national. So these are different, grams of CO2 equivalent per kilowatt hour for these, right? So these are different categories of materials. So some of the generic profiles, again, these are modeled by One-Click LCA, generic profiles. And let's just use the Canada National, which is about 150 grams of CO2 per kilowatt hour, assumed as like the kind of reference point. So 0% difference from the reference point. And then, for example, if you use the BC grid, so you drop from 150 down to like 44 for the grid, you can see for some impact categories of material, there's more percent difference than others. So high impact materials, it's what you would expect. So for example, aluminum, very highly dependent on electricity. So you could see the biggest delta on aluminum cladding, for example. Reinforcement steel, so rebar, typically coming from electric arc furnace steel, so electricity driven process, so that you could see bigger impacts. But then, for things like ready mix concrete, not as big of an impact because it's not as much of an electricity driven process. Not electricity is typically not the main energy driver of like the kilns and whatnot, right? So all this to highlight like just to give a sense of this, right? So like and then if you went to Alberta, which is a higher grid intensity, this is the deltas you see there. That's kind of just an overview of that. Then One-Click LCA also has different service lifespan scenarios. So by default, they use the technical service lifespan. So they have the same assumption for a given material category. They also have things like commercial service lifespans. So if you can imagine like in a commercial office setting, you have more frequent tenant improvements and like more frequent kind of refreshes. So it's not the service lifespan may not be as driven by just technically how long that material can last, but maybe it's more driven by like the commercial cycle or typical service lifespan in a commercial setting. They also have product specific service life. So this is in the cases where there's EPDs where they actually report some reference service life. It'll just show whatever value is assumed in that EPD. And then RICS, just for comparison's sakes, RICS is a standard in the UK. They have default guidance on this. And so I actually looked at all four of these scenarios just to get a sense for these different categories of materials. Again, this is not to say like what's the best scenario or whatnot, but this is useful information to kind of highlight as we're thinking through how do we want to, if we were to create national standard default guidance on service lifespans, how do we model this? What type of values do we see for different categories of materials? Should we break it up between technical versus commercial, for example? There's a series of questions for us to explore. So similar way of structuring that B4 graph as I showed you earlier, but now just the different colors represent those different scenarios. The baseline, the default that is typically used in One-Click LCA is the technical service lifespan. So we're showing that for, like let's say in this case, this is different types of flooring, carpet, laminate, or whatever. You can see the ranges and the number of replacements. And so especially for interior finishes, probably for MEP, those types of things, where you have more frequent refresh cycles, I think it's important to look at those assumptions. less so for like structural materials, which typically last the lifespan of the building. Okay, and then finally, or not finally, one-click LCA end of life scenarios. As I mentioned, if you actually have the expert tier license, which is their higher tier license, you can change the end of life pathway for different materials. And so so we basically tried to highlight what are the end of life pathways that are available to different categories of materials. And so this section is kind of like those categories that I showed you earlier, the downcycling, landfilling, incineration, recycling for different types of materials. And then for each of the material categories, I just highlighted like whether or not like which end of life pathway was available for each one. So that's what the star is. It's just showing like what are the available end of life pathways available for each material category. Now in this case, the way one click models it is like they assume 100% like of the material follows just one end of life pathway. They don't do the kind of mixed end of life pathway thing that like Athena and Tally do, where they say like, oh, for wood in Tally is like 63% gets landfilled or certain percentage gets 22% gets incinerated or whatever. They don't do that. And those are kind of based on national averages and whatnot. Whereas in this case, I mean, they're thinking more probably like for an actual building, it just all goes into one end of life pathway. But also, how do you select what that end of life pathway is? So this is just highlighting what are the range of end of life pathways, and then the emissions figures there. You can see, I mean, most numbers are very low, and then for one pathway, it's very high. This is incineration of plastic. So for some reason, or not for some reason, but like what I've noticed is that like any plastic space product in one-click LCA by default gets modeled with incineration of plastic. They assume it gets incinerated, and it's a very high end of life impact. And so that can affect things like, any plastic space, like so for like foam insulation, or I've seen like rubber underlayment or something like that can have like very unexpectedly high end of life impacts there. So if you kind of take out that data point, and then the other end of life pathways, they're usually below 50 kilograms of CO2 per ton, but then that's kind of these numbers, there are definitely differences in these numbers versus like Athena and Tally numbers as well. So all that to highlight there's discrepancies. Okay, and then last section before we get to conclusion. For EC3, for those of you that use EC3, you're probably familiar with this uncertainty adjusted GWP. So by default, when you're using EC3 currently, they'd show you the uncertainty adjusted GWP values. These values are different from the reported GWP values that are actually shown in the EPDs. So if you have a manufacturer specific EPD or an industry average EPD, you actually have to go through you have to go through extra effort, and in the EC3 interface, select this dropdown, show reported GWP, and then this new column shows up. The reported GWP is the actual reported GWP from the EPD itself. And as you can imagine, there's big differences in these numbers, right? Because this uncertainty adjusted number is like they're adding some uncertainty factor on top of it. So it's a higher number, right? And so we just wanted to understand like what's the scale of the uncertainty adjustments that are used here. For policy purposes, you also need, if you're allowing the use of EC3, you need to specify which report to use. So currently, like they have multiple different Excel exports, but then the policy report is the only one that actually shows the reported GWP. So this is just an example of like tool-specific nuances. As you develop policies, you want to give guidance around this. So those recorded tutorial videos for City of Vancouver that I mentioned, like I also walk through some of this, right? And for context, EC3 is working on a version 2 right now. I was in some of their feedback sessions. They are going to shift away from uncertainty adjusted GWP, I believe, and will focus more on reported GWP in the future, in the next iteration. But right now, the way the uncertainty adjusted GWP, it's based on various different things like product uncertainty, facility uncertainty, like how supply chain specific is the data. And they have a way of calculating each of these categories. And depending on each EPD, like essentially how supply chain specific is that data. That's one of the factors is that determines the uncertainty factor. So this is for all for material categories as defined in EC3, like kind of the higher level material category, the parent category. You can see the range in uncertainty factors that they add on top. The red ones are product-specific EPDs. The blue ones are industry-wide EPDs. So for the industry-wide EPDs, typically they're a higher percent difference or uncertainty factor, like 34%, for example, depending on the category of material. And that's because it's obviously not as specific as like getting a manufacturer specific EPD. And if you, it's like, let's say it's ready mix concrete from a specific batch from a specific plant, that's obviously a lot more specific for what product goes into that facility, that project, versus like some generic industry average at a national level, right? So that's kind of what that is. Okay, the fun part, conclusion. I know that was quite a bit of content to go through. So what are the key insights? First off, the data source is a primary, like a big driver of the variations in the GWP in the A1 to A3. So you know how I mentioned there's like generic material profiles, for example, in Athena and Tally, versus like the industry average EPDs. Obviously, you're going to get discrepancies in those numbers if when comparing that, right? And sometimes there's like regional differences. Sometimes it's not as representative, where you're just limited by what data is available in the tool. So the data source obviously is a big impact on the A1 to A3. Then, you know, most of these tools, they have default modeling assumptions for the later life cycle stages that they just kind of generally apply for each category of material. And so there's obviously variations in that we've seen, you know, in the transport distance and the service lifespans and the construction waste and the end of life modeling. So all these will, so even if your A1 to A3 numbers are the same, you can still have variations in these later life cycle stages. Those other impact categories beyond GWP, there's a significant amount of volatility, like many orders of magnitude differences. So we'd recommend policy not rely too heavily on, or not point too heavily on that, because there's just too much discrepancy to kind of really develop policy around that, I would say. Biogenic carbon modeling, there's some inconsistency in how that's modeled across the different tools, so there should be some alignment on that. And sometimes there's some tool-specific features that can also further affect the results. Even if everything else lines up, you know, you have Click LCA's localization feature or EC3's uncertainty adjusted GWP. Those can also drive some additional variations in the results. So what are the recommendations? How do we kind of improve alignment moving forward? Well, first off, I think if you think about a tool like EC3 and Click LCA, they have like hundreds of thousands of data points. It's very hard to drive alignment on all of that. But I think what we can do is, if you think about from a whole building LCA perspective, can we standardize on just the baseline data, the baseline material data? So if you're modeling a baseline whole building LCA and you're generally using industry average EPDs or a generic profile, can we standardize on what those numbers should be? And generally, I think they should be the latest industry average EPD. So a great starting point would be CLF's Material Baselines 2025 report. They have for 70 product categories, what is the latest industry average EPD? What's the reference for that? What's the value for that? I think we should build off of that, and if we need to kind of add to that or whatnot, but just basically, there should be a standardized list for each category of material. Like if you're using ready-mix concrete in Canada, you need to use the latest industry average EPD for your specific province, like BC or Alberta or whatever, and use this value, the baseline value, for example, right? So there's crystal clear guidance on that. And then beyond that, we should make sure that all of those data points are available in all of the tools. So and then we even go as far as to say, like, what is the name of that data point in that tool? How, because they have different naming conventions for data points. So you can imagine an Excel spreadsheet or a table that just says, like, for this tool, this is what it means. And we verify that all of those data points actually have the same A1 to A3 values, so that there's like a little quality assurance. I think nailing that down will go a long way in improving the alignment. To actually do quality assurance checks on every single product specific EPD is probably too hard, but I think that this is a very manageable thing that we could do, of just being crystal clear what the baseline data is for every category of material. Then the next thing is we should develop national default assumptions for per life cycle stage. So from A4, A5, B4, and Module C, create default modeling assumptions that the tools should use. And I emphasize that these are just the default assumptions. I'm not saying that this every project needs to use these numbers, and like even if they have better data. Of course, like if you have better project specific data, there should the tools should allow the user to manually override that and kind of apply that. If you have better data on transport distances for your actual project for this material from this supplier, you should be able to input that, right? But these default assumptions actually really matter because they are very often used in the tools, right? Or by the different practitioners. And especially in the earlier design phases, before you get through procurement, when you don't actually know which supplier you're going with, and you're in design development or you're submitting for a building permit, for your whole building, let's say for a building permit, you may not have clarity on all this stuff. And so people will use the default assumptions. And if all the tools use different default assumptions, they're going to lead to different results, right? So we should standardize on that. And then biogenic carbon consistency, I think we should also kind of create some clarity around how to model that per life cycle stage, and then also tool specific guidance to the extent that that's relevant. Maybe those are more in practitioner's guide or whatnot. Um, on a high level, this is what I think we should do. So what's kind of a more detailed breakdown of those recommendations? What are the next steps? I think the ideal next steps is that we create a national technical working group to develop what those default modeling assumptions should be from module A4 to C in Canada. So probably bring together a relevant group of people that have expertise in this. It can include the tool providers. It can include experts that have good understanding of like these specific life cycle stages, like surface lifespans for different materials or something like that. Probably the most effective way is to find some sort of consultant or somebody to like kind of lead this work, where they initially look through the data from this analysis, so from this report, but then also look at what other data exists. What's the best available transport data for Canada? What's the best available service lifespan data? Maybe it's not in anything that's actually used by any of these tools right now. So how do we kind of compile all that information and then use that as the basis to come up with the first draft of what these default assumptions are? And then we get the technical working group to kind of comment on this and kind of, and then there should probably be some sort of public comment period at some point as well. But I think just trying to structure this in a way that's really efficient, that's not like trying to bring too many people to the table and get alignment all at once, but but also just trying to get the best available information on that. I think if we can kind of create that, that would be good. Probably requires some funding to kind of initiate this process, but I think that would be good. And then, assuming we have these default assumptions, then you want to update the relevant standards to point to these default assumptions. So, I was one of the co-authors of the National Whole Building LCA Practitioner's Guide from the National Research Council. It gives guidance on baseline definition, et cetera, but that's a practitioner's guide, right? There's also standards being developed, like ASHRAE 240P. There's discussion of like, should we create a national standard as well for whole building LCA, an updated version that code can kind of reference. Regardless, whatever relevant standards or practitioners guides, they should be updated to kind of point to whatever these default assumptions are, and basically mandate that, like, for projects following this policy or this type of standard, they need to have these default assumptions embedded in those tools. We want to validate the baseline material data. We want to define what baseline material data should be. So I mentioned that CLF material baseline report, build off of something like that, point out what are the latest industry average EPDs, be very clear what those baseline data points should be, and then actually do some quality assurance checks and make sure for all the tools they actually show that. This is a bit of a different thing, is that I think it would also be helpful to develop some software compliance criteria for Canadian policy. So like, obviously there's many new tools cropping up. I'm not saying like these 5 tools cover every single tool on the market. There's obviously other tools being developed, and some of it builds off of EC3 data or some other data source or whatever. So we need some criteria, some standardized criteria for like what tools are accepted to be used. So what should that criteria be? Who should review that and approve for Canadian use? So that's another thing. And then I just want to highlight that this is a particularly useful there's a time window of opportunity in that in 2026 right now, we are seeing some major updates across all of these tools. EC3 is working on their version 2.0. Tally is also working on their version 2.0. Athena is working on and has a beta of their web app, an update. Beam is also working on an updated web app as well. And Click LCA is constantly improving, and there's ongoing updates there. So in this cycle, I think there's a unique opportunity to, if we're going to create these default assumptions, to actually have all the tool providers adopt this. I was part of organizing the National Embodied Carbon Summit last year, and we had representatives from all the tool providers, and also just throughout the course of this project, as I was kind of interacting with each of the tool providers. I think there's definitely an openness across all the tool providers that if there is some national default kind of standard list, they're willing, or they're open to like incorporating that in their tools, right? So I think there's a unique opportunity. It is actually very feasible, I think, to actually drive this alignment. Now, everything I mentioned here was like for Canada specifically, but I think it's worth also thinking through what does that look like for the US as well? Is there a parallel process happening in the US, et cetera? So, yeah, with all that said, that's it for me. And happy to take any questions that come from. Oh, I need some water too. So I think what would be best is I'm sure there's probably oh yeah there's definitely some chats. I have not looked at the chat at all, but I my recommendation or my yeah I would appreciate if whoever wants to ask their question, even if you typed in your question, to actually just raise your hand, and then we'll just go through that. And I will actually just stop sharing so we can kind of see each other. Um, so if you have a question, please raise your hand, and then you can unmute yourself, and we'll just I'll call on you, and then we'll unmute. Uh, let's see. Let me close the. Any questions? Anybody? And also beyond questions, I'd also like to kind of brainstorm a bit. If you have any comments about like steps moving forward, like what does this look like for the US, or like or who should be involved in these technical groups, or do you know of good data sources that would be useful for like transport distance or these later life cycle stages? Any other comments as well, beyond questions as well? I'm happy to address that. Okay, we got some. So Forrest, you want to go first?
Yeah, thanks, Anthony.
Oh, just give me
You,
1 second. I think my speaker just turned on. Okay. Yeah. Can you say something?
yeah, you there?
Okay, perfect. Great.
Great. You looked at these different tools and the emissions associated with each of the stages.
Yeah.
Did you look at real projects and how the different tools used on the same project would give what the results from those different tools would be? I'm just trying to understand if
Yeah.
what the sensitivity is there, or what the risk is, especially this is our current state of
Yeah.
the industry in the tool user uses, and if you have, I mean, those the recommendations you put forward will help to mitigate that risk. But did you quantify what that risk is as far as like
So
the
we
results and regulatory policy current landscape?
yeah, great question. So short answer is no. We did actually cite some examples in the, I think it's the introduction, the project overview or the executive summary somewhere in there. We did actually highlight like like for example, Zebex had some case study. I think there was some study done before. There's huge variations in the results, but I think uh, it was due to various factors. The biggest factor in that case study was like I think the XPS installation and how that was modeled in the different tools, which we know there are big discrepancies in. But there, I've seen like a wide range of different studies. So I think you're going to see studies that will say, oh, like maybe it's like less than 10% difference, maybe less than 5% difference. And then another study will show like, oh, it's like 2 times bigger or something like that. And I've seen like a whole range of these types of results. And the reality is that it's very contextually specific to what that project is, what the material quantities are, and then also like which specific EPDs. Maybe there were some like certain data points in that EPD that was like that or sorry that certain yeah EPDs or materials that were defined that actually drove most of that impact or the difference, like the XPS modeling, for example, right? But we explicitly didn't focus on that at the project level because we already know that there can be discrepancies, and we've seen many studies with that. And sometimes it's big, sometimes it's small. It's very context specific. But I feel like we never got to the source of where those discrepancies came from, and more importantly, how do we what do we do about it, right? We can do a million case studies and say like there's a bunch of discrepancies, but then it's like, okay, well, who's going to do something about this? How do we actually like reduce that in the future, right? And so I think that's what we're addressing. I should also say like, this study is at the material level. There are other sources of potential discrepancies in the tools that are not just at the material level. Maybe it's like even how they do the quantity takeoffs. We have like different ways of like, I don't know, or maybe how they do the unit conversions from one unit to another unit. Like what are the default densities they assume, or I don't know. There's a bunch of things that, or if they have some default assembly builder or whatever, what are the quantities that are default assumed there versus like how it might be modeled in another tool. So there are I'm not saying this is every source of discrepancy, but at the data level of like at the material level, this is what we were trying to highlight. Cool. Thanks for that. Morgan?
Yeah, thanks, Anthony. Great work as always. I put a question in the chat there. Curious if you've done an analysis or even a back of the envelope estimate, those top three recommendations you make, if those were enacted, how much, how much of the differences would that take care of? Would
Sorry,
that
repeat that last sentence. I
you
just
so you named three
yeah,
recommendations.
yeah,
If those happened, if those were followed through,
yeah.
how much of the discrepancy would that eliminate? Would that would
I,
would
I
that
I
start
would
to make
imagine
them?
it's most so imagine like you're talking about the baseline building, like you're modeling a baseline project. I
Yeah,
feel like that would be most of it, right? Like because like you're
yeah,
defining what is the baseline material, so you got the same A1 to A3, and then if you have alignment on all those later life cycle stages, and all the and you verified that, and those assumptions apply for all the data points in a given material category in the tool, right? So then if you can do that, you should theoretically eliminate most of it. Again, I think there's still edge cases, there's still, or not just edge cases, there's still like, for example, material quantities or how things are built up. There are other tool specific nuances that could probably lead to some discrepancies, but my sense is like those are probably the biggest ones. And if there's some
yeah,
like tool specific things that they're doing that will further adjust the results, that obviously if you can kind of give guidance on that and reduce that, I feel like it would address most of them. Yeah.
yeah. Fantastic. Thanks.
Yeah. Thanks. Claire.
Hello, hi. Yeah, I posted a little bit in the chat, and I know some of the people involved in the work that I'm doing with SE 2050 are also on the call. But I just wanted to flag that we are currently, I don't know if some people on the call are familiar with the iStruct's embodied carbon calculator,
Mm,
which is built based on RICS, one of the guidance that you mentioned, as you can probably can tell
hmm.
from my accent. That's where I hail from.
Oh, awesome.
Um, and I have been working with both Canadian and American kind of groups, kind of CLF, SE 2050 kind of crossovers, lots of stuff going on to basically adapt that tool for North American usage. And it just kind of comes from a place of very much A1 to A5. We're not trying to do whole
Yep.
building LCA takeouts necessarily. There's lots of arguments for how and when you should do that, but it's just kind of early making design decisions and changes.
Yep.
And the main task that we're focused on at the moment is doing that like standardized list of like your basic assumptions of A1 to A3 values. So taking the industry averages,
Yep.
regionalizing them where it makes sense and not regionalizing them where it doesn't make sense, like where it doesn't kind of make any difference, or it's you're going to be um, kind of generally taking the slightly more conservative assumption. And yeah, we're also going to have to kind of build a transport calculator because the UK one is it's a tiny country.
Yeah. Yeah.
Everything's either coming from very close by or very far away.
Yeah.
Whereas obviously North America, it's a very different kettle of fish.
Hmm.
So yeah, I think I just wanted to flag that really. I think it maybe would act as like a good stepping stone for some of the wider works. And also I like to advocate for doing a national standard a la RICS for Canada because I
Mm.
really miss it.
Yeah. Totally.
I miss people approaching everything in the same way. And it means that you know, I guess we have to ask ourselves why are we doing these in the first place, right? Is it so that you
Yeah.
can market your building as green? Is it so you can comply with some building compliance things? Like, why are you doing it? And then
Yeah.
ergo, how accurate does it actually need to be? Like, what are you trying to compare? What are you trying to use it for?
Mm.
Um, I don't have an answer, but just thought I'd throw that out
No,
there.
that's great. Yeah, no, thanks for flagging that. Yeah, it's good for me to know that. I think it's, I'll also say that, so here, like in this report, we're kind of comparing, I mentioned that we're comparing, like what the tools already assume, right? Like they might cite different things. For example, for
Hmm.
transport distance, like I think Tally assumed, like looks at the US commodity flow survey in 2012.
Hmm.
And then like I think EC3 looks at like the US commodity flow survey in 2017. And there was just a 2022 update, but I don't know.
Hmm.
Is that the best source? Do we have a Canadian specific source? What should we use for there? But then there's additional research. So I know in this University of Washington, like their life cycle lab, Masa there like did a presentation at Greenbuild about like for A4, they're creating a much more nuanced way of like how to model A4 emissions as well, right? So
Hmm.
there's like kind of
Hmm.
other research being done. I think there's some research being done on end of life as well. So like I think there's a few different sources of potential information. So we want to kind of like figure out what's the best available thing, but also what's the at the right level of granularity and practicality for that can be kind of easily referenced in a standard, right? So
Yeah.
yeah, I think there definitely should be some coordination on yeah, all the different groups because I think this is of interest to many different groups, not just like the Canadian government, right? So but yeah, thanks
For
for your
sure.
comment. Okay, John.
Good day, sir.
Hey,
And
good seeing you.
nice long time no see.
Yes.
Um, yeah, I'm in a bit of a different role than I was last time, so
Yep.
nice to engage in this space. I guess like so. Thanks again. A really really interesting analysis, and kind of I think drives at some of the core of what I'm thinking about. Um, and I'm coming at it again from a bit of a different angle, but maybe jumping on the same horse I have historically.
Mm,
I'm really interested in understanding where we take this kind of analysis and where we take, like in the context of a policy space. So as currently representing Canadian steel producers, I'm thinking about how do we make this easy to get actuals. And it was very when I was at Housing Infrastructure and Communities Canada, we were doing a bit of we're kind of opposite end, trying to validate and look at the impact on actual projects and understand what made a difference. But it goes a bit to that space of like, okay, what kind of not just policy, but what kind of technology, what kind of digital backbone do we need to actually move this to a more specific space where we can actually get more consistent real results that map to actuals. And part of that is
So
like
when you say actuals, what do you mean? Like
well,
transport, actual transport, or what actual?
so the transports gets quite interesting, but it tends to be like, at least in steel's case tends to be a very minor element. But when we talk about whether it's like the construction, some analysis that I've seen done suggested that the construction space was actually quite significant in terms of the overall emissions,
Yeah.
maybe underestimated relative to what we would think.
Yeah.
So there's that dimension, but so getting enabling like real data
Yeah.
go from there, but then also enabling um, the more direct use of EPDs from specific producers. Because, for example, like regional steel EPDs don't really make sense. But you can have specific product EPDs from a steel producer that are
Hmm. Hmm.
drastically different from another. Like
Yeah.
even the same
Yeah.
facility could produce two entirely different steels. So that's the kind of thing where it's like, oh, okay, interesting on if you're actually tagging the actual goods digitally, like is that something where we see down the road? Is that 10 years down the road? Is that 20 years down the road? Like, what do we look?
Yeah.
What do we thinking? Anyway, just
Um,
maybe a bit out of left field, but
Yeah,
that's
no, I think the short answer is like I think these things can, if it's straightforward enough to kind of integrate this. First off, like if you have if steel producers have like great data on like for example the waste factors to use or like the transport distance or how we like I think we would definitely be like assuming this technical group gets involved or whatever, and like we start working towards something like this, definitely that type of feedback would be useful of like, what's the best way of modeling this for, and these are things that like the different materials industry associations or whatnot are probably like very well positioned to answer. So the to the point that like you can kind of give good Canadian specific data. If you have project specific data, that's great. A5, I know like some of the nine biggest GC or some of the nine of the GCs in Canada have gotten together and they're actually tracking across 600 projects, looking at
yeah,
A5 emissions and stuff. So like, maybe
yeah.
we can look to them. Maybe they can give some actual good, like better default assumptions to use for like site energy use or something like that. So basically, if you have input on like what are better defaults to use, I think there should when this process moves forward, I think ideally like yeah, being able to contribute that will help inform that effort. Yeah. I just noticed we're actually kind of short. I'm happy to stay longer, but I also want to be respectful of people's time. So I'm happy to stay as long to answer the questions, but I'll try to go through them more quickly. So, Ivan?
Yeah, thanks, Anthony. This
Yeah,
is a great presentation, great reports.
thanks.
I was wondering what questions coming from more of a policy perspective. What, how do you, how how ready do you think the tools are to kind of allow us to kind of enter customized inputs for these baseline assumptions, like the transportation distances, what we do with end of life, the split of 100%, like all in one mode versus split between different modes of
Yeah.
disposal, all these things. Because that's, to me, it basically, I think for policy, we need to have that common baseline, and we can argue what that baseline is, but across the tools, you should be able to customize it if we that's a kind of a lower hanging fruit, I kind of think, for us to do that, to enable us to
Yeah.
do that, to make those comparisons. Yeah.
So I think in terms of the standardization of like the defaults, I think like all the tools should be able to accommodate that, especially the upcoming updated versions of this as they're being developed. I think if this process kind of moves forward kind of relatively quickly, there's a great opportunity to kind of make sure that those tools are developed such that they can kind of model this properly or like in alignment with whatever the gets decided on like the standard approach to doing this. So I think that should be quite feasible. And then whether they have manual overrides, if you have like better project specific data, I think most of them should have that as well, that capability. So I don't think it's like a major issue that like whether the software tools will be capable. I think the current generation of them, yes, there are challenges with it, but I think with the upcoming versions of many of these, they should be able to handle that.
And are they kind of expecting to do that? Like, are we expecting
Well,
them to
I've
allow
talked to
to
the
open that?
five tool providers. I think that they all express
Yeah.
openness in this, and like it's it's not also in their interest to see a bunch of discrepancy in the results in all the tools, right?
Yeah.
Like they don't want to be. It's not like they think this is like their proprietary thing that like these assumptions are what differentiate them. Like they want like alignment ideally, right? Because that's actually what's going to move policy forward, right? If the whole
Yep.
industry and like policy actually has confidence in the results, that's better for everyone. That actually helps it proliferate. If everyone's like, oh, I don't know if I can trust these results or whatever, then like that's actually what's going to like stall progress and have this actually not move further forward, right?
Yep.
So yeah,
Great.
thanks for
Great. Thanks.
Azadeh? Azadeh? I'm sorry, I'm not sure if I'm
Yes.
pronouncing. Yeah.
First of all, thank you so much for the
Mhm.
presentation. My questions are just from a supply chain perspective, because this carbon tools is also really good from a supply chain perspective. I wanted to know that which one is more better and which maybe more applicable for a Canadian system. Yeah.
Sorry, from a supply chain perspective,
Yeah.
which tool is more or is it
Yeah, you mean the numbers, I mean, that they calculate, because I know that the focus is in carbon but let's say that to see the better or realistic supply chain, I mean, which one? Because, I mean, for carbon, I mean, life cycle emission, they have to see the supply chain, but I wanted to know which one is more better from this.
sorry, so you're saying for something beyond carbon? So like what is there some other metric that when you say like which one is better on what dimension? Like for what?
Yeah, because it is, I mean, this is actually the step before the carbon. I mean, let's say that before they wanted to calculate carbons, I mean, they should see the supply chain, and then based on that, the energy that is consumed or material, and then multiplied by
Yeah.
let's say this carbon
Yeah.
emission factors, right? This is a system. But the better that they consider the supply chain, the better that they are. So, I mean, maybe my question is that which one better consider the supply
Okay.
chain?
I mean, if you're saying like, let's say you're like which manufacturer you're going with, and like assuming that they have an environmental product declaration that they produced,
Yeah.
then I would say in that scenario, probably the tools like at least currently EC3 and Click LCA, they have, as you saw, like the biggest database, and they have many of those manufacturer specific EPDs. So those tools are likely to be the places where you can find like the most specific data to your like what you actually procure.
And
Where versus like using some generic profiles from another tool, right?
yeah, thank you so much. And then only, I mean, EC3 is available free for use, because
Hmm.
I mean, I checked the other ones.
Yep.
They only give the demo version to use,
Yep. Yep. Yeah. EC3 is the free to use, and yeah, Click LCA is paid.
and
Yeah.
it's better for the Canadian systems, I mean, to use.
Uh, I mean they all have
So,
different strengths and weaknesses. I'm not going to say which tool is better.
oh, okay,
Yeah.
fine.
But
Thank you.
yeah. I think those two tools are for your
Thank you,
what you're
Professor.
asking
Thank
for. I
you.
think is
Thank you.
yeah. Akna.
Hi, Anthony. Thank you
Yeah.
for the presentation of the study. Seeing that there's variability in the results and this need for harmonization of methodologies, which is something that is being spoken of in Europe as well. I'm based in Spain, so I'm curious about like further next steps on a more general sense. Do you know if in other countries that have LCA requirements, do they do like some sort of audit or verification of the calculations?
Of
Since we're heading
the
towards like
calculations from
policy.
like the practitioner or the consultant, or you mean audit or verification of the software tools?
No, of the results of
Of
the
the results?
LCA. Yeah.
Good point. Or sorry, good question. I'm actually not as familiar what is the
Mm-hmm.
current practice in Europe. This is something that I have advocated for. I think like part of the reason why
Mm-hmm.
I've been a strong proponent, like both in City of Vancouver, but also just any jurisdiction that have embodied carbon or whole building LCA requirements or embodied carbon, like project level embodied carbon requirements, is for them to collect the raw data, which includes the material quantities
Mm-hmm.
and you know what specific data point they're using, like what EPD or whatever. When you get that kind of spreadsheet, the raw data, regardless of how it's formatted, I think that is extremely useful because basically, if you get that data, then you can both do much more robust benchmarking, so across all the submissions, but also importantly, it actually opens up the possibility of creating automated quality assurance checks when you have that raw data, right? Because if you're just reporting like some flat value, like you know the total GWP of this project is like 400 kilograms of CO2 per meter squared. Like that's great, but I can't really verify anything, right? So like if you actually get the raw data, then there's a bunch of checks you could check, right? Like did you specify like your baseline definition is the same as what we think the baseline definition should be, what data point that's called in the tool, and like there's a bunch of things that you can kind of check for. So I think there's definitely a strong possibility for that, and that's definitely important for like building code implementation or any sort of policy implementation to reduce the effort from like any building official or anybody that's reviewing this to not have to be an expert and review in detail every single thing, right? But so all that to say is that I think that's also something that there are many people in this space in North America that are also, I think, thinking about. But in terms of examples, I'm not sure. Maybe some in Europe, I'm not sure. But
Perfect. Thank you very much.
yeah. Okay. I mean, as I mentioned, I think this is if I'm happy to go longer. If anybody wants to leave or needs to leave, feel free to leave. But I prefer people could actually, if you did type in a question and you want to raise your hand, that'd be great. If not, I can kind of maybe just quickly scroll through just to see if there's any major things. I haven't looked at the comments at all or the chat. Yeah, this presentation will be recorded. It'll be shared. Let me just take a quick look if there's anything else. Actually, I mean, this might be too much to go through. If there's anybody, if I didn't get to address any of your questions, please like raise your hand. But if not, then we'll end the call here. Let's see. All right, I think we're good.
I can
Great.
also, Anthony, if you want, I can flag a couple of the questions if you wanted.
Oh,
Or if you just want to end the call, that's okay too.
I'm not sure if I've seen many, some of them are different comments.
Jeremy had a
Okay, feel free to
like,
email me afterwards as well if you have any further questions, but yeah, I think we'll just end the call here. Thank you so much. I appreciate your time and attention, and yeah, thanks. Bye. All right.